Okay. All right. So basically, just as a quick overview, we're going to be going over all the quizzes, the practice quizzes and your actual quizzes, 1 and 2. And then we're going to do your practice exam 1 and your exam 1 from this semester. And so I'm hoping that while you're watching this, you can have your everything open in front of you as well as we're going through it, because I'm not going to be showing the actual quizzes on my screen. I'm just going to be working through a few problems. So let's go ahead and start with the practice quiz 1, 2019. And so in the first one, they're asking you for some Lewis structures. I think maybe we can do like one of these. Let's do the first one, 1A from quiz 1, practice quiz 1. So they're asking you for it's CH3, CH3, COOH. So one trick that I like is that every time you see a CH3, and you guys are totally familiar with this now, but you guys didn't really know this when you first came from Gen Chem, that carbons generally, like, you'll see the structure a lot where it's, oh, this is a CH2, because that doesn't make any sense. So carbons can have this like structure of CH3 and then C, and that's kind of like a chain. It's like a carbon chain. And so the CH2 is going to have another 2 hydrogens on it, and then it will be attached to another carbon. So that fulfills octet of both of the carbons. And then you have another carbon that's attached to 2 oxygens and a hydrogens in there somehow. And this is a structure you'll kind of learn to see, and I'm sure you guys are already like seeing it a little bit. So one of the oxygens is double bonded and the other oxygen is single bonded. The single bonded oxygen can have a hydrogen on it, right? But I'm just going to denote that because this is like a Lewis structure in Dr. Son's style. So you kind of have to draw your bonds between everything. And so this is going to have 2 lone pairs if you're going to make it fill octet. And the other one is also going to have 2 lone pairs. Any questions about that? You guys are good? Okay. And then obviously there's no charges here, so you don't need to include that. Everything's pretty nicely balanced. So the way that you can check the electrons of your molecule and make sure that there's no charges is, first of all, like, you can just come up here to the name right here, right? Or the molecular formula, and you can kind of like figure out how many valence electrons each of these atoms has. So carbon typically has 4, right? Hydrogen will have 1 each, but there's 3 of them, so that's 3 for hydrogen, right? And then 4 for that carbon, 2 for those 2 hydrogens, 4 for this other carbon, and then 6 for each of the 2 oxygens. I'll just write that as 12, and then 1 more for that hydrogen. So let's just add that all up. 14, 15, 19, 23, 26, and 30. Okay. Does that add up, guys? 30?
Yeah.
Valence electrons? Okay, cool. So then you can just go through and you can count them. So each each bond is going to be 2 electrons, right? Because there's 1 electron at the carbon end and 1 electron at the hydrogen end, and they're making like a covalent bond. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then we have 22, 24, 26, 28, and 30. So there we know that this is like the correct Lewis structure, because there's 30 valence electrons in total for the molecule, draw the Lewis structure, and also the molecular formula up here. All right. So that's just the basics of your Lewis structures. The second question has resonance, but I'm sure you guys know how to do resonance. After the break, if you have any questions about resonance, you can let me know. But resonance, you're just flipping your double bonds around. So I guess I can do this example out real quick. So there's like a N. So this is the second question in the practice quiz. And this is just your typical resonance thing. So you start out with a positive charge on this, a negative charge on this oxygen, and no charge on anything else. And then basically what you're doing is you're just gonna take, because there's so many like lone pairs on this oxygen on the right that they start kind of crowding up and they can lead to this resonance where it creates a double bond there. Oh, sorry, I forgot to mention the two lone pairs there. And then basically, because that breaks the octet of nitrogen, um, the 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 bond there, the double bond, is forced to become lone pairs. The pi bond, it just breaks up and becomes lone pairs. And so then you just get like the opposite, the exact same thing, but the opposite. So it's the double bond is on this side, and your single bond is on this side with all the crowded electrons. And then again, there's just going to be that switching back and forth. So that's why you denote it with this going back and forth arrow between them. It's not a one-sided arrow.
Fatima, just to clarify, this doesn't have anything to do with question 1B, right?
No, this was no. This is 2. This is question 2.
Oh, okay, thank you.
Okay. Yeah. Okay. So I'm gonna move on to question 3 because I think this is really important, and a lot of you guys have forgotten this by now. Because I received like a lot of questions about this before the last exam, so it'll be good to review it. So this is this is like a series of questions where he's gonna ask you, where you basically have to know like how many double bonds and stuff are there. So it's kind of like a way of switching back and forth between bond line structures and molecular formulas. If you're given a molecular formula, you can figure out how your bond line structure is using this technique. So the question here is, he gives you this molecule, right? So it starts out as this like ring with 3 of them. So like and then it comes down here. There's a double bond, and then there's a triple bond here. So this is like a little bit complicated because he's asking, what is the molecular formula? And so for molecular formula, you could just go ahead and count, right? And I recommend you do count. What I'm going to count is I'm going to count the number of carbons. So there's 1 here, right? So that's 1. There's another here, 2, 3, 4, 5, 6, 7, 8, 9, right? So there's 9 carbons. That part is easy. But how do we know how many hydrogens there are there? Well, we could count, but counting hydrogens is like a long, tedious, kind of process, because there's so many hydrogens compared to carbons a lot, right? So counting carbons is something that you should be able to do really easily all the time, because it's kind of critical for when you're doing like synthesis and stuff like that. But if you want to count your hydrogens, a little bit more involved. So there's this molecular formula or there's this formula you guys can remember about the degrees of unsaturation. So if we have, so Cn and H2n plus 2. So basically N stands for the number of carbons. So it says that if you have N number of carbons and the hydrogens is double that number of carbons plus 2, then that is equal to 0 degrees of unsaturation. And then for each degree of saturation, you just subtract 2. So if it's Cn and then H is 2n without the plus 2, then that is 1 degree of unsaturation. If you have Cn H2n minus 2, that is 2 degrees of unsaturation. Okay? But all you have to remember is just remember this first one, that 0 degrees of unsaturation is Cn H2n plus 2. That means that unsaturation is basically anything that is going to be a ring or a double bond or a triple bond or a pi bond. So basically a ring. So a ring equals 1 degree of unsaturation. Doesn't matter if it's a ring with 3 or if it's a ring with 20. Any ring is 1 degree of saturation. Also, a double bond, is 1 degree of saturation. And a triple bond, because a triple bond contains 2 pi bonds, right? Like this. A triple bond is going to be 2 degrees of unsaturation, because it's just 2 pi bonds. So each pi bond and each ring count as 1 degree of unsaturation. So going from that, all we have to do is go back to our original drawing and kind of figure out how many degrees of unsaturation does our original drawing have. Mubaraka, do you want to walk me through this?
Yes. I have 1 ring,
Yeah.
1 double bond, and 1 triple bond. That means I have 1, 2, 3, 4 degrees of unsaturation.
4 degrees of unsaturation, right? Because
Mhm.
we have 3 pi bonds in all, right? We have 2 of
Mhm.
them here,
Yes.
and then we have 1 here. And then we
Mhm.
also have a ring up at the top left.
Yes.
So this is going to turn out to be
4.
4 degrees of unsaturation. So going from that, we know that so our number of carbons is 9, right?
Yes.
So with any degrees of unsaturation, how many hydrogens do we need?
2 and plus 2 into 9 plus 2.
Yes, which is
20.
20, right? So without any degree of saturation, so 0 degrees of unsaturation, it's going to be H20. But
Yeah.
here we have 4 degrees of unsaturation.
So
Now,
my
remember what I said. For each degree of unsaturation, you take away how many hydrogens?
2. Oh, 1
No, 2. 2.
or 2.
Yeah.
Oh,
For
yeah.
each degree of unsaturation, you take away 2 hydrogens.
Mhm.
So 4 degrees of unsaturation, we take away how many hydrogens?
8.
Yeah, exactly.
1, 2, 3, 4. 8.
So that means that our formula is what? It's C9 H20
12.
minus 8,
12.
12. Exactly.
Mm-hmm.
So this is our answer, and it's like that basically. Now I know that you can just count it as well, and I might count it if you had extra time just to make sure you did everything right. But this technique is actually really important because you need it later for determining isomers. When he gives you a molecular formula and he says draw all the possible isomers, you'll need to know whether those isomers have any degrees of unsaturation. If so, how many, right? So I would recommend just using this technique as well to practice it because you'll need it. And we'll probably end up going over that today as well. Okay, so here, I mean, this is something new that he kind of introduced, which is question number 4 in the practice exam. It's something new that he kind of introduced recently. It's basically like doing resonance with a bond line structure, and people found that really difficult. And I can see why, because it's like very I don't know, like it involves moving lone pairs when you're not used to seeing lone pairs in bond line structures, right? So the first structure he draws you, it looks like this. And there's a double bond right here. Then there's a plus charge right here, over here. And I think that everyone should review this because I think he might include this in the exam for sure. So essentially what's happening is that he's asking you what is the more stable resonance form of this. Now, anytime you're looking at this, a good bet would be to take care of those positive charge carbocations. And the only time that I said you don't want to like move something onto the end. Do you remember that, Julie? What did I say? I said, remember I used to say this thing about not moving things to the end because you'll lose a hydrogen?
Yeah, because then it'll take the hydrogen off.
Yeah, because you'll be removing a hydrogen by introducing a double bond to the end. So if there's something you notice about the end, so I'm going to draw a chain that has 2 ends. One of them is double bonded, one of them isn't. Now, if you look at this end of the double bond, how many hydrogens are there? There's 3, right?
Yes.
But if you look at this end of the double bond, there are just 2.
2.
Right? So one thing that I said about this that you guys should remember is don't move double bonds onto the very last one because then you're getting rid of a hydrogen. And we don't want to do that, you know? Getting rid of hydrogens will be like changing the number of hydrogens in general is not what he's looking for. He's asking for the same exact molecule, just a different resonance form of it, right? So be careful with these hydrogens. Make sure you don't move a double bond. So like, for example, if I had a double bond right here, don't move this double bond onto the end, because then what you get is you get this situation where you've kicked off a hydrogen. So now you only have 2 hydrogens here, and we don't want that. Okay. So going back to up here, let's draw a resonance form of this. So what we get, so we do want to take care of this carbocation though, because it's you know, it's right there. So let's just go here, take that double bond there. Let me do this in red. We're going to take the double bond onto here. And then something that can always happen in your resonance, which is pretty good to do, is take care of the uncrowding around oxygens and stuff, the crowding around oxygens. So there's a lot of lone pairs up there. So if you take one down and form a double bond for that oxygen, it'll take care of that negative charge on the oxygen as well. So what we kind of get is much more stable because it has no charges. And remember that it's better to have no charges. That kind of indicates, I mean, I don't know. It kind of is a good idea for your resonance to do that. So basically what happens is we've taken care of that carbocation, and also we have created a double bond here, so the oxygen has no charge, neither does the carbocation anymore. So what we end up with is something that has completely no charges anywhere. And when I'm looking at the answer key, this is something I remember a lot of you guys were asking about before as well. Like, there's no need to mess with any double bonds on this end because they're not a part of the resonance. Okay? They're not a part of the resonance. So there's no need to move that around or anything. It's just we're working with the areas that need to be taken care of. In general, those are areas that have charges, areas that have like a lot of lone pair crowding, stuff like that. Okay, and then after that, he goes about like decreasing acidity. I think you guys can probably handle that. Do you guys have any questions about that, or are you good?
I am.
Go ahead.
No, I said I'm fine.
You're fine? Okay, cool.
I still had questions about acidity. Not like acidity as in like the molecules that are listed over here, but like acidity in general.
Yes, yes.
I'm still not like super clear on why something is more acidic than something else, like based on what shape it is.
Yes, okay. So
yeah.
I could go over that. That's a great idea to go over that. So there's a few things that, so there's this type of question right here, question number 5, practice quiz 1. There's that kind of question where it's like, you know, he's just listing like a couple of atoms and basically he's asking which one's more acidic. That stuff is like, you know, Gen Chem, probably remember that stuff pretty easily. But the new stuff is like when he gives you organic compounds and asks which one is more acidic. And so it's based off of 4 things. Do you guys remember this? Is this what you want me to go over, Julie?
Yes, that is exactly what I want you to go over.
Okay.
I remember one of them is like resonance.
Yes, one of them is resonance, yeah. Okay, so the first thing that's most important is, gosh. Okay, I have my list. It's somewhere up here, but this document is a mess, a complete mess. So I'm gonna try to find it on Husky CT, maybe, because I went over it before. But so there are 4 factors, right? And they are the atom, right? Atom, resonance, what else?
Was it like polarity or like molecular?
What do you call that? Induction, inductive effect, right? Yeah.
Yes, yes.
Inductive effect. There's one more. Inductive effect.
I read hybridization.
It was 1 is atom, 2 is resonance, 3
Hybridization.
is
Wait, sorry, Locke, your voice is really, really low. Yes.
Oh, wait, hold on 1 second.
Because I'm trying to find my notes and I can't remember the exact order right now.
Yeah, the way you've written in notes are atom next to each in question, and then you wrote bond length, electronegativity under it, and then inductive effect, hybridization, conjugation.
Okay. Wait, conjugation.
So like resonance.
Yeah, conjugation is a little like resonance, yeah. So I think that's kind of what I meant there. Okay, So yes, okay. So effects. So now I'm gonna put them in order though. So atom is definitely number one. I'm just looking it up because I remember I wasn't sure when I wrote those notes which one was first. Second is resonance. Okay, that's right. Third, because this is in terms of importance. Third most important. Where are we? Oh yeah. Then okay. So I wrote these in order actually. Okay, that's cool. Interesting. All right, so these are the 4 factors of acidity in order. And what I'm going to do is I'm just going to go through them and explain. So atom, you guys mostly know, it's basically what that question was asking. So atom is the hydrogen that's going to leave, because acidity is all about hydrogens leaving, right? Acidity is all about the willingness to give up a hydrogen, to donate a hydrogen, okay? So basically, so the first one is about that hydrogen that's going to leave, the atom that it's attached to, how willing is that atom to give up a hydrogen? And as you can imagine, that's definitely the most important factor. So the way that acidity works on the periodic table, right, is that it goes in this direction and then in this direction, with this direction being primary and this direction being secondary. So um, essentially what it is that so atoms that are, let's say, going down, atoms that are farther down are more likely to have a strong acid, be involved in strong acids, than atoms that are farther to the top. Also, atoms that are farther to the right are more likely to be involved in acids than on the left. So an example between, let's just do something simple, HBr and HI. So I is actually farther down than Br. If you pull up a periodic table, it looks like, and by now this is something that we should all know, I is beneath Br. So basically I is going to be your stronger acid. HI is going to be a stronger acid in this case because I is farther down. And this has to do with bond length, right? And it's just the simple fact that I has a wider bond length, so it's more likely to be stable after the hydrogen's gone. Whereas Br is like slightly smaller bond length, so it's less likely to be unstable. So bond length is definitely the most important aspect. And so when I say number one, the most important is atom, bond length is actually the most important within that. And then secondary to that is electronegativity. So once we've figured out bond length, let's say there's 2 things that have pretty much equivalent bond length. So for example, let's have OH and NH. They're both in the same, like, what do you call this, period group? I don't know. Across, basically. They're both in the same, this is how the periodic table kind of looks. It looks like CNOF, the parts that we need to know at least. Cl, Bri. Something that would be worth adding there is an S. That usually comes in handy, knowing where S is. So essentially, you see that O and N are actually right next to each other in the same group, period. I don't know what you want to call it. Group. No, period. So basically, that means that they have similar bond lengths because bond lengths are shared across this way. So O and N have similar bond lengths, and so that means that what the next most important thing to take into account is electronegativity. And oxygen is more electronegative than nitrogen. So electronegativity, that's your second thing that's most important. Within, again, we're still talking about within the atom. So that's the first aspect. And even if you see like a whole bunch of organic molecules, if you saw like something that was like long and complicated and I don't know, it had like an OH here versus something that was, I don't know, an NH, you'd still just to follow the same basic principle. These molecules are both the same in terms of everything else. And the most important factor is the atom right next to it, next to the hydrogen that's leaving. So you would circle this one as being more acidic. Sorry. You'd circle this one as being more acidic. All right. Okay, so let's move on to the second factor, which is going to be resonance. So with resonance, the more resonance is basically the better. I remember something weird came up with this, guys. Do you remember when you have like a ring that has complete resonance around it already, then it's not acidic though. So basically, from what I remember, you know, if you're given this kind of situation where it's a carbon here, double bonded oxygen, single bonded oxygen, this is your typical, you know, your typical acid configuration. Um, so basically, I'm just going to erase these lone pairs. But basically, what's going to happen is that you're just going to create this resonance around here. Actually, no, never mind. We need them. So you're just going to create this resonance around here. So the lone pair comes there, and then that goes up, right? You've seen this a million times. But basically, this resonance, it makes it more acidic than something that's like this. I don't know. That just has like, I don't know. I don't know. I don't know. An O, OH, and then that's it. Maybe. You know what I mean? So this one has no resonance, the one on the right. So this one would be more acidic. But I remember that there was this one thing that happened which was a little bit weird, maybe on the practice exam or something. If you have like a ring that has complete resonance around it already, that one is less acidic. Okay? So I'm trying to find that now. Do you guys remember this, what I'm talking about?
I remember it. It was like a cyclohexane with
yes.
yeah, with like really weird positioning, I guess, of the double bonds.
Yes.
And I think like specifically because of where the double bonds were positioned.
Well, I don't think that was it. Because okay, so basically
because it was every other bond exactly, right?
Yes, yeah. So when I say it's not about the specific positioning exactly, but it is the fact that we have complete conjugation already inside of the ring. So I found the example. It's the last question of your practice exam. No, of your actual. Wait just a second. Yeah, of your actual exam. The last bonus question. So it's this versus this, right? And this one already has complete resonance going around in it. Like there is since it's completely conjugated in there, you can't take a double bond, a lone pair down and form a double bond. That's impossible because there's no room for that to go anywhere. Do you guys see what I'm saying? Kind of like you can't really bring a double bond down there because it's just gonna it has nowhere to go. But let's take this example real quick. So you take your lone pair down, and this just switches over to a different spot, right? And so what you get is you get a double bonded O, right? And you just get a lone pair here, right? So this one is more acidic. Wait just a second. Now I'm confused because of the answer key. Huh, okay. So I think we're gonna, do you guys see what I'm looking at right now? The last question of your actual exam. It's really confusing because I can't even tell where the person got their points because they only got 4 points. And I think they got this one wrong. Let me check mine.
Yeah, I have no idea what's going on in question D. I think it's actually maybe my bonus points page, because my bonus points page was a disaster and it looks a lot like what's going on over there.
Interesting. Okay. So I think I got this question because I've been doing the exams with you guys. Interesting. I don't know if I got it right either, actually. This is so weird. I think I got it wrong. I'm not sure. Okay, we're gonna have to put a pin on this and see what the actual answer is because I cannot tell from the answer key or from my exam what the correct answer is.
Yeah, I'm 500% I got this question wrong because least basic just means strongest acid if I put an H on it.
Yes, and it seems wrong because I'm pretty sure that this one is more acidic. Like, this one has no resonance at all. Like, it can't, you know? Or I mean, I don't know. We'll see.
Right, but I thought because the S is attached to it,
Yeah,
or is attached to B, like S has to beat O, right?
yeah, I definitely agree that S should be more acidic than O for sure. Just because of bond length. But I'm just confused about the difference between A and D. Um, is it that A is first? I'm confused. Is D maybe the most acidic? I'm not sure.
There's
I would
also a
think D
question
is most.
exactly like this on like the front page of your guys, like the fall 2019 exam.
So the last page too, or where? The
It was
front page?
like, gosh, it was really far in the front. It was like the first or the second page.
Oh, okay, I see it now. Yes. Okay, okay.
Yeah.
So he's saying that but this one is a little different. So this one looks like, okay, so we're gonna have to put a pin on this and talk to Dr. San for a little bit about what's going on here. But
Oh
this one
no.
is basically an OH here with a, two double bonds and an OH with just one bond. So again, if you just envision everything happening, um, I don't know, he's saying that there's no resonance here in this situation because let's say you kicked off the hydrogen, right? Which is all what acidity is all about. Then let's say our lone pair went down, nothing would happen. You would just get this and with two lone pairs here. So nothing would happen. Nothing would be forced to move. But in this situation, you take off your hydrogen and the lone pair comes down onto here. But that forces the double bond to move, right? So what we get is this.
Yeah, so it looks like it's a question of like being able to kick the double bonds
Yes.
around.
Which is why I believe that this one is more acidic than the other one. Because this one involves some resonance. This one on the left can't involve any more resonance than it already has.
Does it have anything to do with like conjugation?
I think yes. Yes, to a certain extent. Because like if it's more conjugated, there's gonna be more like flipping around of double bonds. But in this situation it's completely conjugated. And since the ring, like there's no opportunity for the double bonds to even move anywhere, really. Okay. So we're gonna ask him about this question in particular because I'm surprised. I guess we didn't really address it back then because it was like, like I don't think anyone was really thinking as far ahead of the final at that point. We just kind of wanted to move on, but it's really important to know because it's like, I don't know. Now we're looking at the final, we're not sure from the answer key or anything. But let's move on to inductive effect.
Okay. Out of everything in the whole class, this is the part I'm the most worried about.
Yeah, this is really tough. I think resonance in particular has been the hardest. I would say out of all the other things, inductive effect, hybridization, that kind of stuff is really, really easy when he asks it. But hybridization is resonance is the most kind of intricate idea. So let's just move on to inductive effect. So inductive effect is the idea that some kind of electronegative molecule within or some kind of electronegative atom within a molecule can help hold some of the negative charge. So as you guys know, electronegative atoms, they prefer, like they're called electronegative because they like negative charges. So the idea is that, let's say we had some kind of molecule where, I don't know, let's just make OH the part that's going to lose the hydrogen, right? So I'm just going to duplicate this. And by the way, it's going to end in 5 minutes. So just, let's take, I don't know, let's come back at 2:30 because I do want to charge up my pencil some more. And I'm going to string these two videos together. But anyways,
Okay.
So let's say that there was some kind of, like very electronegative molecule in here. And in the one case, it's only 2 carbons away from the OH, but in the other case, it's many more carbons away from the H. It's 4 carbons away, right? So basically, or I don't know if you want to call that whatever, but basically it's farther away from the OH. So in this case, the F is going to step up and absorb some of that negative charge when the hydrogen leaves. So you can think of this one as being more acidic because it has higher inductive effect. All right. So that's kind of one example he'll ask you guys. Sometimes it'll be more about distance. Is that electronegative molecule closer or farther away from the OH or whatever, the SH, whatever you want to have it be. Another option is sometimes he'll give you the same thing, but the difference will be in the fact that we have an F and an N. So if you look at it like in the periodic table, it goes CNOF, right? So F is the most electronegative, N is least electronegative out of the two. So that means that F is going to be the one with F is going to be a better acid than the one with N. So I think this is the main two questions you can ask about this. It'll either be about distance or it'll be about the type of atom and how electronegative it is. Okay. I think that covers it. Next, we have hybridization. This part is also really straightforward. Hybridization, it's just like, you know, SPS, SP2, SP, SP2, SP3, so forth and so on. So I have a question right here from your guys' actual exam. It's question number 10B from the actual exam this semester. So it's asking between a couple of different things, and this is like the only situation I've seen him ask it, by the way. So there's not much to remember here. But basically he has this molecule which has lost the hydrogen, obviously. And then a double bonded one, right? And then a single bonded one. Okay, so what's going on here is this should have a hydrogen, right? I don't think he drew that right.
The question was
right
strong. Was this question was the strongest base though?
Yes, strong at base. But shouldn't that Okay. Okay, so going back, so this is where we ended the last video. Hybridization. We're talking about hybridization and how it's influences acidity and basicity of molecules. And so what we've got here before us, like this question from the actual exam, question number 10B. So he's asking about the strongest base, but I'm pretty sure that this is supposed to be a hydrogen right here. There's supposed to be one hydrogen, and a lone pair with a negative charge. But anyway, so basically, all we have to look about here is hybridization. And so the only thing that's important to know is that the most acidic is the one that has the least hybridization, or the highest potential of acids, whatever you want to call it. So I'm just going to write down the hybridization of each of these carbons. So this carbon is just going to be sp, because it only has this hybridization situation. It's all about areas of electron density. And so these triple bonds together, they all create one area of electron density. The lone and two lone pairs, like one lone pair, I guess, is another area of electron density. So since it only has two areas of electron density, it's sp. Now, moving on to the second example, this one has the one area of electron density from the double bonds, another area of electron density between it and the hydrogen, and I'm going to draw this out. So basically, it's another area of electron density here between it and the hydrogen, and then a third area of electron density in the lone pairs. So this is going to be, the hybridization of this one is sp2, because it's an S and then two P's, right? So that's three of them. And if you want to think about it this way, you could just write like SPP 1, 2, 3. Okay, so there's three areas of electron density. It's going to be sp2. For the third one, it's one area of electron density there, and then I'm going to rewrite these hydrogens the way that they are, like in terms of bonds. So there's one hydrogen and then another hydrogen, right? So there's one area of electron density between the two carbons, another one between the first hydrogen, and another one between the third hydrogen, the second hydrogen. So that's 3 areas of electron density, and then the lone pair here, that's a 4th area of electron density. So when I draw this out, it's going to be sp3. So 4 areas of electron density altogether. Okay. And so basically, all you have to remember is that sp is more acidic than sp2, which is more acidic than sp3. Okay. And so that's one way of thinking about it. But another way of thinking about it that Dr. Son likes is the percentage of S. So the percent of it, the higher the percentage of S, the better. And I'll show you what I'm talking about. So in SP, it's 50% is S, right? So that is going to be more acidic than this SP2, where it's actually only, what is it, like 35, right? No, 33%. Am I doing this right? Yeah.
Yes.
33% is S, right? Because it's like SPP, right? And so when you have SPP, this is only a third of the entire thing. Whereas when it was SP, it was half of the entire thing, right? Now that's going to be more acidic than SP3, in which case it's 25% of the entire thing because it's SPPP. And so S is 1/4, right, of the entire thing. So you can think of it either in terms of just this, like SP is more acidic than SP3, or you could think of it in terms of the percentage of S. The higher the percentage of S, the more acidic it is, okay? And so for basicity, it would just be the opposite. So going back up to this previous question right here, if he's asking about which one is more basic, then you would just go with the opposite. So the most acidic would be this one right here because SP. So you're just going to go with the opposite, which is SP3 is going to be the most basic. Okay. Any questions?
Just to clarify, this is hybridization, the lowest importance.
The lowest importance, yeah.
Okay.
Okay. Next, there's a question about, so we're still on practice quiz 1, but we just took that little diversion. But basically, the last question of practice quiz 1 is about a dipole moment. So I think this is all about recognizing what a dipole moment is, how to get that, and then basically also how to do your Lewis structures and figuring out the shape of your Lewis structures. So essentially, when it boils down, and you can see from the answer key pretty clearly, what it boils down to is we have like a C with 3 Cl's and a hydrogen versus C with 3 Cl's and a fluorine. And so Cl's and fluorines are pretty equivalent, right? Compared to Cl's and hydrogens, right? So there's way more of a difference between Cl and hydrogen than Cl and fluorine. So the Cl's and fluorines kind of end up balancing each other out. So this is nonpolar. But this one, it is polar because this hydrogen has like very little impact. So overall, the molecule does have a strong polarity. Okay. Okay. So I think that's it for that quiz. Let's move on to the actual quiz 1. So for the actual quiz 1, just starts out with which one's the strongest base. We're going to skip that. Second one, what's the molecular formula of the following bond line representation? We already went over an example of that. We showed you a complicated bond, a complicated bond line structure, and then you have to give us the molecular formula. But I think it wouldn't hurt to go over this one, just because this stuff is really important, the kind of like technique behind it. So it's kind of hard for me to see because I'm looking at the key, but I think it goes like this. Yeah, I think this is what it is. Okay, so let's just count our carbons first, which is the first step you have to do. You can't get away with not counting the carbon. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 carbons. And then all we have to do is let's figure out with 0 degrees of unsaturation how many hydrogens it would need. So Lakshmi, what if there were no degrees on saturation? How many hydrogens would there be?
If there was no degrees, then 24 hydrogens.
24. Yes, because, and this just all comes from our formula, which is CnH2n plus 2. So the H2n plus 2 part gives you how, like, that'll be with 0 degrees of unsaturation, right? But in this case, we do have a few degrees of saturation. What do we have?
A ring and a double bond.
A ring and a double bond, because there's a ring going around here, and then there's also a double bond within there. So that's 2 degrees of unsaturation. So how many hydrogens should I subtract from this original H24?
4.
4, yes. So that means that our actual molecular formula is C11H20, right? So that's it. I mean, it's pretty simple. But very, very, very important. Okay. Next is a Lewis structure. I think we can skip that. Another one about polarity. This is pretty much the same stuff. Definitely check out those resonance ones though, because like a lot of people have trouble with the resonance. And when I'm looking at these resonance, do you guys think there's anything that you want to go over from those 2 resonance questions? No? I'm having a hard time, to be honest, because I'm looking at the answer key. I'm having a hard time seeing what was originally there. But yeah.
I remember, like, for this, the top part of the answer key, it's definitely mine, and I know mine was a disaster of comments. Because I think there's like a mistake in there that really, really confused me.
Yes, there
So, like,
was a mistake.
I did the problem like 2 separate times because I didn't know what he meant.
No, okay. I think that lone pair wasn't meant to be there. So we're talking right now about question 5B in the actual quiz from this semester. And so he starts out like this.
Oh my gosh, I remember this. This was
Yeah,
traumatic.
everyone was so upset afterwards. So, and I think that might have been meant to be a double bond, guys. Like seriously, it was crazy. Okay, yeah, that was supposed to be a double bond. Oh my god, it did not look like a double bond at all. So what he drew was this. But what he actually meant was, oh, and there's a negative charge here. And it made no sense because of the negative charge. So, what was actually supposed to be there was a double bonded oxygen, and that changes everything. Because all you have to do with these lone pairs is kind of create like a double bond here, and that pushes these up. And it's that simple. And that's the answer. But unfortunately, the way that it was drawn was not clear to everyone at all.
Yeah.
But this is basically the answer. So if you recognize the mistakes in the original drawing, it won't be too bad. I mean, looking back, that line was a little thick, but I just assumed it was a single bond, but whatever. Okay, so that's that. Do you guys have any questions about that question still, or is it clear now that we know the mistakes that were drawn originally? Okay.
Could you go over number 4?
4. Okay, so for 4, he basically states that CO2 has no dipole moment, so it's non-polar, right? Non-polar. God, okay. And he says that SO2 is polar. So basically we have to, as usual, draw Lewis structures to show how polarity is. And so when you kind of draw CO2, you draw, so again, one thing I like to start out with is with our electrons. So C has 4, and then 2 oxygens are going to have 12 together, right? So that's going to be 16 electrons. SO2, on the other hand, well, S has 6 electrons on its own. So it's basically 6 times 3, right? So it's 18. So essentially we have 18 electrons and 16 electrons. So let's start with our CO2. So you might just start by drawing, 2 oxygens attached to a carbon, right? And then you might start trying to fit those, lone pairs in. We know that we need to add up to 16, right? We need to add up to 16 valence electrons altogether. So far we have 4, 2 in each of those bonds. So let's just start adding lone pairs, maybe a double bond here or there. So that becomes 6 out of 16 used. And then, that oxygen typically has 2 lone pairs on it. So that's 6, that's 7, 8, and that's 9, 10. And then let's go ahead and add some here. 11, 12, 13, 14, and then 15, 16, right? Because we know that the carbon needs to be filled in terms of octet, right? So that kind of makes everything work out. Our carbon has the octet filled, our oxygens have their octet filled, and the electrons equal 16, which is great. Let's do SO2 now. So SO2, let's just start out with the same process. We have the 2 oxygens on each side. We're gonna start adding our double bonds. You can kind of do, it's like a trial and error type thing. But look at S. S needs an octet filled. How can we fill the octet of S? Because S's octet is to have 6 things attached, just like an oxygen. So as of now, it's only attached to 4 things. Do you see this, Lakshmi?
Yeah, I see it.
Because where is sulfur in the periodic table? It's it goes like CNOF, and then S is right underneath O. So S and O both need 6. They need to be attached to 6 things to have a neutral charge. So this is not gonna cut it. S needs maybe like it needs like another, like a lone pair there. Do you see that?
Yeah.
Now it has 6 things because when you count it, it's like 1, 2, 3, 4, 5, 6. So it has 6 valence in its valence shell right now. So that's good for sulfur now. Now let's just backtrack a little bit, count up our valence electrons, see how many we have left. So that's 2, 4, 6, 8, 10, 12, 14. So we need to get 4 more electrons in there. So we can probably just do this, right? And that gives us our structure. So again, if you look at this, all the octets are filled nicely. Our valence electrons are, working out perfectly. We have 18 valence electrons. So what you'll notice is that this one has a lone pair here in the middle. So that's going to change its shape actually. So what it's really going to look like is this. It's going to have this bent structure, right? Whereas this one is linear because there's no lone pairs here. So it's just going to remain flat and straight. But this one, SO2 on the other hand, is going to be bent. And so essentially what this means is that this one, you can explain it this way, this one is going to have a polarity to it because those 2 oxygens are facing in a different direction, and we have this kind of end here, which is like, doesn't have anything pulling on it, whereas this one, it has 2 completely opposite forces, so they'll just end up canceling each other out and we get nothing going on here. Like it's equal poles in the opposite direction. But this one has 2 poles that are going downwards. There's 2 poles going downwards, so overall has a polarity going down, but nothing going up, so to cancel it out. Does that make sense?
Yeah, I understand it now. Thank you.
Wait a second. Do you guys see this? My Lewis structure for the SO2 is different than the answer key. I must have done something wrong.
Does S does not have to fill the octet? I thought only CNOF has to fulfill octet. I made the structure same as you, But
Yeah.
do you need positive and negative charges?
I don't really understand why the person had to do it the way they did.
I made it the way you
Yours,
did.
right? Julie, is this your answer key? Oh, Julie's not. Okay.
I'm here. Sorry, I forgot to unmute.
Oh, no, it's fine.
No, it doesn't really matter because it's just going to be conjugated a different way. I think your
Right,
guy's drawing is definitely more stable. It doesn't
Yeah.
matter though because it's just a resonance structure.
Yeah, and anyways, it still has that like polar structure to it, even if it like you switch around the charges and stuff. So I guess it doesn't matter whether you do it according to like what the answer key did or this way if you find this more like if this makes more sense to you. But either way, you'll find that there's a some kind of structural difference there where the lone pair on the sulfur makes it bent. So then you get this polarity happening.
Yeah, like full disclosure, guys, I am really, really, really bad at Lewis structures. So I always draw like 2 or 3 resonance structures before I get like the actual stable structure.
Yeah, but either way, it worked. I'm exactly the same. I think I'm just starting to get a handle on Lewis structures like exactly 2 years after I learned about them. So for the first time. So yeah. All right. So I think this is looking good. Let's move on to your practice quiz 2. So then what we're doing here is we're introducing IUPAC naming, which is really cool. So from what I found, there's a few different ways he asks IUPAC naming. So he can give you a bond line structure and ask you for the name. That's definitely going to happen on your exam. So let's just take one of these examples. Let's do since you guys are, pros now, let's just take this, it's 1B on your practice quiz. Okay. So I like this because it involves, the cyclohexane. So I'm just going to walk through this example and then I'll have you guys, walk through a couple of examples as well. So the way that we start out with our, our circles is we need to determine which one is going to be the first carbon. So when I'm looking at this, I think that this carbon right here is going to be carbon number 1. Because you have to choose carbon number 1 to be the carbon that has the most things attached to it, right? And now you guys, from later on, double bonds, oxygens, that also plays, a role as well. But this is, back from exam 1. We don't know about that stuff yet. But carbon number 1 has the most things attached to it. And then we're just going to go in the direction that's going to have something attached to it next. So we're going to go 2, 3. If we had decided to go counterclockwise, right, it would have been 2, 3, 4 before we got to the next thing, right? So that's why we go the clockwise direction here. Okay? And so that's carbon number 3, and this is carbon number 4. So then let's just go ahead and name it. So as you know from like naming, I kind of like to do like a list first. So I'm gonna start out with my 1,1 di bromo, and then I'm gonna have my 3 ethyl and my 4 methyl. And then I'm just gonna put it all together. So like, and also there's the cyclohexane. So then I'm just going to put it all together according to alphabetic order. So 1,1 dibromo is going to be the first. Then we have the, as always, the ethyl goes next because that's the next alphabetically speaking. And then the methyl is going to go after that. And then you can just put your cyclohexane. Cool. All right, so let's do another example. Julie, do you want to walk through this one? I'm choosing 1C right now.
Yeah, I minimized the window and can no longer find it because I have 8 of them open.
Oh. Sounds a lot like me. Okay.
Yeah. So 1C, right? You have to start with finding the longest chain.
Mm-hmm.
So like I'll arbitrarily start with like the one that's sticking out of the top, the furthest up, and I'll start counting 1, 2, 3, 4, 5, 6, 7, 8.
Mm-hmm.
So it's some kind of octane. And then
Yeah.
I'll figure out what will give me like the lowest numbers,
Mm-hmm.
like the maximum number of lowest numbers.
Yes.
So if I start counting from the left, it would be like 1, 2 methyl. If I start counting from the right, it will also be 1, 2 methyl. However, from the right, if I start
Wait,
counting,
sorry, just a second.
did we?
What do you mean 1, 2 methyl?
So it would be like 1, 2, and then on the third one would be a methyl.
Oh, okay, yes. So there would be a 3 methyl.
Yes, and then if you count on the other side, it would also be a 3 methyl. So you have to go to like the next thing that's closest, which if you're counting from the left, you get the Br and the ethyl first.
Yes.
So
Mhm. Continue.
you would count from the right, and you would start numbering from the right. So it would be like
So
the 1,
let me
2.
just backtrack for a
Yeah.
second. So so this is a little complicated to explain, but basically
Yeah.
we have these groups coming off of the chain, right? And so I'm gonna do from left to right in green. So our first thing would be at a 3. So we have something at a 3. 4, 5, we'd have 2 things at a 5. And we'd have one thing at a 6, at the 6th carbon. Now let's just do this in yellow from the other direction. So again, that first methyl, this one, would be at carbon number 3. Why am I doing this way? 3. The next one would be at 4. The next 2 of them would be at 4. And the last one would be at 6, right? So if you look at this one goes 3, 4, 4, whereas this one goes 3, 5, 5. So it's better to choose this option where everything is closer to the beginning of the chain. You know, you have a 3 and then you have a 4 and a 4. But in the other one, you have a 3 and then you skip 1, and so it's farther away. So overall, the idea is that everything is more conjugated towards this end of the chain. Everything is closer to that end of the chain. So it's best to start from where, Julie?
Yes, I apologize. It's much easier to explain if you can draw it out like that.
Yeah, exactly. That's why I just but go ahead.
So going on from that, I would then like go through and alphabetize it. So it's like so it's like a bromo, there's an ethyl, and there's 2 methyls.
Right.
So because of that, I would start with the 4 bromo,
Okay, sorry, just a second. 4 bromo.
the 4 and then go to 4 ethyl.
Mm-hmm.
And then the 3, 6 dimethyl.
Perfect.
And then the octane at the end.
Yeah, okay, that works. So this is our answer. So basically, so Julie just put everything in order in terms of alphabetical order and stuff like that. You put your 2 methyls together. So anything that's the same functional group, you put them together. So you put your methyl that's on the 3, your methyl that's on the 6, you put them together and call it dimethyl. Okay. I think that's good. I just wanted to do an example that had chains within chains. So let's skip to number 2 on the same practice quiz. Number 2 has chains within chains, and it's also great because it has this whole condensed formula looking thing. So it starts out with CH3, CH2, CH2. Goodness, there's 6 of them. Okay, CH2, CH2, and then CH. 1, 2, 3, 4, 5, 6. Okay, and then these are each attached to these branches. This one has. This is such a pain. Okay. And then the other one has, okay. So when he asks you for IUPAC name of a condensed formula looking thing, you absolutely have to turn it into IUPAC first to see it. to really see what's going on there. Well, I mean, I don't know if you absolutely have to, but you should definitely turn it into a bond line structure first to be able to give it an IUPAC name. So the thing that I like to do, and that Dr. Zahn recommends as well, is to just count the longest chain of carbons that you see here. Now, this isn't necessarily your longest chain of carbons, period. But that's a good start. So I'm just gonna draw my 6 carbons. And then we know that from this 6th carbon right here, we have another chain that continues down here. So let's just draw that, right? So this chain has 1, 2, 3, 4 carbons. So I'm just going to continue. This is my 6th carbon here, and I'm just going to denote that like that. So that's 1, 2, 3, 4. 4 more carbons coming off of it. And then again, from this same carbon, so I'm just going to make it have this like heavy dot because we need to know where it is. From the same carbon that's right here, it has another thing coming off of it that goes, it has 1 carbon, another carbon, and that carbon is attached to 2 CH3s. So 1 carbon, another carbon, and that carbon is attached to 2 CH3s. So you just do it like that. So then you can just go ahead and do your IUPAC naming. Lakshmi, do you want to do this one?
Sure. I don't know if I remember exactly how.
Oh no, that's fine.
Oh wait, which one am I doing?
This.
Oh wait, don't we have to finish adding the bottom part?
Oh no. So yeah, so this was the first 6 of them here. The first 6 going along this.
Oh, okay.
And then from there I just attached this other chain.
Oh, okay, got it. Okay. So I think the longest chain is the one like that you drew out.
Yeah, like this thing.
Yeah.
Yeah.
Yeah. So so I would start from the right and go towards the left.
Yeah, so starting from the right, why?
Because if you go from the left, the what's it called? It would be on 6 instead of 5.
Right.
It says 5 is yeah.
Yeah. So this branch coming off with that, the little whatever you want to call this is closer to the right end than the left end. Okay, so what now?
I don't exactly remember how to do this.
Oh yeah, that's fine. And this one's a little bit more complicated because we haven't done this in a while, to be honest. But there's branches, so that makes it a little bit more complicated.
Is it like 2 comma 2? Wait. Sorry, hold on 1 second. So if you have to renumber that thing that's coming off, right? So
yes,
it would go 1, 2, 3, and it could go to either methyl, and then it would be 2 methyl propyl.
Wow, very good. Yes.
Man, that came back to me. Oh.
No, that was really good. That was really good. But you also have to put this whole thing. So this will have like a, that whole thing is coming off of which carbon of the main branch or the main carbon chain?
Number 5.
Yeah, so this is just what you do. You do 5, and then inside the bracket, to describe what 5 has, it's a methyl on the second of a chain of propyl, basically. And then what's the word that would go at the end here?
Decane.
Decane. Good. Yeah, so that's that. And then the other option is he could go back and he could give you an IPAC and ask you for the bond line structure. So Mubaraka, why don't we do this one? This is a little bit, again, something old kind of, but I'm pretty sure you can, we can get it.
Yes.
So because it has the sec, and I think, it's easy to forget that kind of stuff.
Okay.
Isopropyl cyclopentane. Wow, this is
Cyclopentane. 1,
quite
2, 3, 4, 5.
a mouthful.
1, 2, 3. Okay.
How do you like to start this problem?
First I would make a cyclopentane with 5 carbons.
Mm-hmm.
I would like to number it from the you know how it's like a house, so the one on the top, 1.
Mhm.
And then
Like that?
I can't see. Yes. And then any on the 3. But I only need until 3.
Yeah, okay. Now what?
1 isopropyl. Isopropyl is a Y.
Yeah. Yeah.
Oh, so I would write a Y on 1.
Mm-hmm.
And sec-butyl is it's like a line, and
Yeah.
then 1, 2, 3, 4. It's like 4 carbon, a butane, but on second carbon it's joined.
Okay. So there's 4 carbons overall.
But on the
And
second carbon it was, or the third, I forgot.
Yeah.
It's the second. It is second.
Yeah. So this is the answer. And just remember isopropyl, what was there? There was a few IUPAC 1TS you guys to memorize.
There were 2.
Isopropyl, tert-butyl, sec-butyl, and isobutyl?
I think so.
Did he ask for isobutyl? Yeah. So I think the ones he wanted you to memorize were this one, this one, this one, and possibly this one. I'm not sure. I don't have the list in front of me, but go back and look at your notes and try to memorize those those
4.
names. Yeah, there was only 4 of them. And I can't remember exactly what they were, but I know that these were all definitely there. I'm not sure about this one, if this was. I think it was, though. Okay, so, and they all have specific names that you need to know. But, so this wasn't exactly an IUPAC name. This was more of a common name type thing, hybrid that he gave you. But either way, you have to be able to convert the names into the bond line structures. Okay, let's move on. So, this next question he asks about the hybridization. So again, we're still on practice quiz 2. So he asks about hybridization. I think we can skip that. I kind of explained that earlier, so if you don't understand, just look at the video when it's posted. And then, oh, okay, so oxidation and reduction, we can do this real quick. So in this problem, he gave you this, and he says that it becomes this. So he's asking you, is this oxidation or is this reduction? Oops. Is it oxidation or reduction? So basically, the way that you have to do this in orgo is much simpler. You just count your number of hydrogens. So Julie, do you want to walk through this?
Sure. So if we go off of the one that's on the left, you can see we have 1, 2, 3, 4 carbons.
Yeah.
And then there's like one that's attached to the OH. So I will just count that. So because you have the 4 carbons and one of them is not attached on both sides, like one of them is not a secondary carbon, it would just be like the number of carbons times 2 plus 1, which I think is 9, plus the extra carbon from the H, which is 10. So there's 10 hydrogens.
So you're saying there's 4 carbons. Each carbon has 2. You can always assume
except for the one on the end, which has an extra one.
For the end, yeah, because basically this is a pattern you guys will get to know, but like these each have 2 hydrogens, except for the one at the end that always has 3 hydrogens, right? So
yeah, if it's useful, like literally just draw the hydrogens and count them.
Right, yeah, that's also very possible since this is just a small molecule. but basically there's going to be two hydrogens for each carbon, and there's going to be one at the end, and also this hydrogen right here. So it's going to be 2 times 4 carbons, so that's eight hydrogens, then plus this one and this one, so that gets you to 10 hydrogens. Now, what about this right one?
On the right one,
yeah.
you notice that the fourth carbon is now connected on all 4 sides. All the octets are filled.
Yes.
And there's just like an H that's sticking off of it. If the H was not there, I would say the same thing, except like you have to then draw the H in there.
Mm-hmm.
And so like it's only the other 3 carbons that you would need to like count up all the hydrogens for, and then add a hydrogen at the end. At the end of it, let's see. So that's 1, 2, 3 times 2 is 6, plus 1 is 8. So there's only 8 hydrogens in this one.
Okay, so basically, we're just going to do our 2 hydrogens for each carbon, and then this carbon has 1 additional, and this carbon also has only 1. So it's 6, and the 7th, and then the 8th. So that gives you 8 hydrogens, right? And so now we can compare 8 hydrogens versus 10 hydrogens. So what is this, oxidation or reduction?
Oxidation, because the number of hydrogens has gone down.
Yes. And I, like, you guys might remember this oil rig from before, but I just used it. This was something we used in Gen Chem, but I just use it for Orgo and it works. So, like, you can just think oxidation is it just replaced the I with an H. So it's a loss of hydrogens. Reduction is a gain of hydrogens. Just replace the word ion is with a hydrogen now, and it works. So oxidation is the loss of hydrogens, which here we lost 2 hydrogens, so that's oxidation.
I have a question. Dr. San said something else about oxidation can also be adding oxygens.
Oh, really?
So,
ooh, okay.
yeah, so like, has he ever had a question like that, like come up ever? Or is it always going to be losing
or gaining hydrogens? Yeah.
Yeah.
So from what I've seen, that it's always yes about hydrogens being lost and gained. So just use the hydrogen thing to figure it out.
Okay, because I wasn't sure, because if it's the same number of carbons, but both the number of oxygens and the number of hydrogens go up, then I have no clue what to do.
Right, yeah. No, exactly. I don't know, but I definitely don't think that's gonna happen. Usually he just changes the number of hydrogens around. Because that's all that's really applicable. I mean, I guess you do add oxygens in Orgo too, but the hydrogen thing is especially applicable in Orgo too. Okay, so now we're gonna move on to this boiling point question, which is really important because by now we might have forgotten this. So the first most important thing in boiling point is the number of carbons there, right? So when you look at this question, this is question number 6, practice quiz 2. So when you look at this question, in the answer key, question like the molecule D has 8 carbons, whereas the others only have 7 carbons. So the first most important thing is the number of carbons, and more carbons equals higher boiling point, right? So that's just the first principle. So obviously, if you're looking at the question, D is going to be ranked first because it has 8 carbons. After that, it is the number of branches. And so more branching is equal to a lower boiling point. Okay? So first most important thing, the number of carbons, always look for that first. And the more carbons, the higher the boiling point. Then the number of branches, the more branching, the lower the boiling point. So D goes first because it has the most carbons. Then between A, B, and C, they all have the same number of carbons, so we need to choose between branching. A has the least number of branching, so it's going to be the highest out of the three of them. Between B and C, C has like only one branch coming off, whereas B has two branches coming off. Or is that three branches coming off? Yeah, B has three branches coming off, whereas C only has one. So C is going to be ranked the next highest in terms of boiling point, and then finally B because it's very branched. Okay. Let's see. Okay, so let's move on to this quiz, to the actual quiz, yours actual quiz. So it starts out with some IUPAC naming. We kind of already went over that. And over the break, if you guys like try to study and get stuff in order, and then I think after the break we can pretty much start working on the new material, and you guys can ask me questions about this old stuff. But I'm not going to go through like every single question just because I don't know whether it's important or not. So even if you're watching this video and then you're going to watch it later and stuff, just think about any questions you have from any of the practice quizzes or practice exams, quizzes, whatever. If you have any questions, just write them down, and I'll try to do like a session where we can just do like questions and answers. So I'm kind of scrolling through this. I'm not really seeing anything that's important on the actual quiz too. So do you guys have anything you want to point out from there or no? I would say that if you're someone who has a hard time with condensed formulas to IUPAC naming, on your actual quiz 2, question number 2 is very good for that. It has like a ton of branching. It's very complicated. But do you guys have anything you want to bring up, or are you guys okay?
I am okay.
All right, cool. So let's move on to the practice exam. So first page, we just have a ton of IUPAC naming. And here I just want to point the last one. I don't know if you guys remember Fisher projections that much because we really haven't done them since then. But your Fisher projections basically show down a carbon-carbon connection. So this is so I'm just gonna do this example right here. And remember, this is different than Newman's projections. Don't get those confused. What are Newman's projections, Mubaraka?
The one that you're drawing.
Oh wait, sorry. The one that I'm drawing is the Newman projection. What are the Fisher projections?
Those are the straight lines. The
Straight
one
lines.
with hydrogens are forward or backward.
Yeah, so the Fisher projections are these,
Mm-hmm.
where we always make sure that our hydrogens are like on this plane and they're going forward. So everything horizontal is coming forward, everything vertical is going backwards. And your longest chain typically goes in this direction. So that's a Fisher projection. Don't confuse the two. This Newman projection right here, we have it's looking down a carbon-carbon connection. So the first most important thing when he's asking for an IUPAC name from here is to just do you like your bond line structure first? Like I find that's the most important thing. It's really, really hard to do naming straight from Newman's projection. And you can try just for fun, but on an exam, I would definitely suggest to turn it into a bond line structure first. So what I like to do is I like to start by doing my first 2 carbons. So I'm going to do 1 carbon in green and 1 carbon in yellow. So those are going to be my 2 carbons that I'm looking down. So I think that this one right here is going to be my green carbon, and the yellow one is behind. So starting with my green carbon, what things is it attached to, Lakshmi?
It's connected to a CH2CH3, CCH33, and a CH.
Okay, so this should be a CH3. Yeah, so this is what it looks like. It's attached to a tert, right? It's attached to an ethyl, and it's attached to a methyl. All right. So those are the 3 main things. I just drew them in a weird like situation. They're not exactly the same orientation, but it's fine. So for the orange one, Mubarka, what should I draw there?
CH2, and then
Wait,
a turret.
CH3.
Oh
Wait,
no,
what?
is this CH2? Yeah, CH3, and then again CH3. But there's
Hmm.
two CH3s.
Right.
But there's no.
Okay.
Mhm.
So that's that for the our bond line structure. And then all we have to do from here is we just have to count it up and stuff. All right. So we were just talking about how um, we're dealing with a bond line structure now, and we're gonna be trying to convert this and writing our ID pack name for it. Um, so um, who did I say is gonna? Julie, do you want to do this one?
Okay, sure. So I would start with what I perceive to be the longest chain. However, I think something that's really interesting about this one is that there's theoretically two places where the longest chain could start.
Yeah.
If you see like that tert group that's hanging out the top, you could start carbon number 1 at any of those carbons at the top of the tert group. At the
Hmm.
ethyl that's underneath the green one, you could also start to get a long chain. However, because no matter where you start on the tert group, you're guaranteed to have like a 2-dimethyl. I'm just going to start there because I think that's going to be the least work having to renumber things later.
Well, to backtrack a little bit. So if we made
Yeah.
our carbon chain from starting from here to here, so that would be
Yeah.
1, 2, 3, 4, 5, right? So that would be 5 there. We could also
Yes.
go, so that's in red. I'm gonna do another one in another direction. Let's say we started from here, same, but in orange now, or no, let's do green. So in green, if we started here and we did 2, 3, 4, 5, that's also a 5 chain, right? So there's two options. You can go across this way, or you can go down, like you can come up and around this way. Both of them will have
Yeah.
5. So which one are you going to
And
choose?
the other thing is if you go around the other way, like if you start from a tert and end where the red 5 is currently,
Yes, that's another possibility. So
which is a lot. So you have to kind of like figure out which one will give you the most things. Yeah.
yeah, so there's like 3 possible directions. So I'm just going to erase all of this and draw out the 3 possible directions so that you guys can see it kind of. Um, oops, So essentially what it's going to look like is, and I'll draw them all in different colors. So a red pathway might look like this, like that. And then green, we could go this way. And then yellow, we could go this way. So those are the 3 possible options. Also, you could just go, yeah. So then basically those are the 3 options, and we have to figure out which one is best. So since they all have 5 carbons in them, you have to choose the one that has the most branching closer to the beginning of it. So continue from there, Julie.
So I was going to say, I start with like the tert group that's on the top.
Yeah.
Um,
Mm-hmm.
that could belong to either the green pathway or the orange pathway.
Mm-hmm.
Because that will lead me to like 2-dimethyls, like 2,2-dimethyl
Mm-hmm.
as one of my things. Whereas
Yeah.
if I started from like the secondary group where there's the orange pathway or the red pathway, I would only have one or like a 2-methyl, and there would only be one methyl piece. Does that make
Yes.
sense?
Yes.
Yeah.
So
So I'm going to start
basically,
with the, yeah.
starting from here is better because you have 2 methyls coming off of it. Whereas if you start from this end right here, you're gonna have only 1 methyl coming off of carbon number 2.
Yeah,
Starting
like
from
no matter which
here,
route you're going on.
yeah, starting from this end. So starting from this end, you're gonna have, you can't do that because your first thing attached is gonna be on the 3rd carbon. But so for the other 2 pathways on this side and this side, if you start from either one of those, the first branch is going to come at the second carbon instead of the third carbon. But in the best thing about the starting from the tert group is that you're going to have two things coming off at the second carbon. Whereas if you start from this group, you're going to have only one thing coming off at the second carbon. If you start from this side, you're only going to have one thing coming, you're going to have some things coming off at the third carbon. So that's a no, that's a no. This is the best way to start. Start from the tert group, basically.
Yes. And so the excellent thing is that because of that, we can eliminate the red pathway.
Yes. So eliminating the red pathway means that we know that it's going to go, we know that it's going to, we know that it can't go, wait, what was the red one?
The red one was the one at the very bottom, which was like the
Okay.
U-shaped one.
Yeah, this one, okay.
So we know that
go,
it's...
Julie? Are we going to go here or are we going to go down this way?
So I'm going to say I want to go to the right because that's going to lead to less complicated things to describe. Because in this case, in carbon 1, 2, 3, if you go down, you then have to make something that's going to be like a methyl ethyl, which would be less pleasant to describe than just, you know, a methyl and then an ethyl.
Okay. So basically we've established that that's going to be the first three in the chain. So Julie wants to make this fourth and maybe this fifth, right?
Yeah.
In terms of the chain, instead of this fourth and this fifth. And what I would add is that something that Dr. San actually told us, and this is a rule, is that you want the most number of branches possible. So essentially if we went in this direction down here, which is the wrong one, we would only have 2 branches coming off, or yeah, so we'd have 2 branches coming off, right, at that carbon.
Yeah.
But if
in other words, you should minimize the number of parentheses you need to use.
Yes, exactly. So knowing that, how are we going to name this now? So I'm going to erase these two so that the direction is now shown correctly. We're going to start up at the top, and we're going to end down here. Now what?
So it's a pentane, but the pentane goes at the very end. I would start with the 3-ethyl because ethyl is alphabetically the first. There are
Wait,
1, 2, 3.
I think that'll help.
Yeah, we should. So, firstly, it's a pentane. We know our longest chain has 5. Secondly, we have 4 ethyls, 2, 2, 3, and 4. So that's 2, 2, 3, 4 tetraethyl.
Wait, sorry, did you say methyl or
I mean methyl. I am so sorry.
Okay. Yeah. So counting all of our methyls, we have the 2 methyls here, another methyl here, and a 4th methyl here. So that's going to be 4 methyls, and they're going to look like 2, 2, 3, and 4 methyl, or tetramethyl.
Yeah.
Okay.
If it's helpful, like if you just want to write like what the methyl is, it's just methyl, and then list the places where they are and note that there's 4 of them.
Yes.
If that helps you keep better track and stops you from having to come up with like tetramethyl off the top of your head.
Yeah. Yeah. So you could just write ME. You could do whatever you want to help you like figure out what you're going to have to draw all together, or you could list it out, methyls, and then list out where they are, 2, 2, 3, 4, stuff like that. But then what else?
And then there's an ethyl on carbon 3.
Yeah. So this one was very complicated, actually.
Yeah, so then you just alphabetize them.
So in alphabetical order, we'd start with our ethyl first. So 3-ethyl, and then we have 2, 2, 3, 4 tetra methyl, and then we have our pentane. Okay, that looks good. All right, so
this question was like really complicated, like with the Newman projection and everything.
Yeah, it is. Yeah, because first, I mean, besides the fact that this is a really complicated bond line structure to work with, we started out with a Newton projection, so that makes it even like harder. So I would say this could probably take someone easily like 5 minutes on an exam. Um, so yeah, definitely look out for certain questions like this. Very tough. Going on, I'm just seeing some questions about acids, bases, pKa. So in case you forgot, I don't know. A higher pKa. So when you have a higher pKa, that is equal to what? More basic, right? So just remember this. Higher pKa is more basic, lower pKa is more acidic. pKa is very much similar to pH. So we know that like lower pH equals lower pKa, which equals more basic or more acidic. However you want to think about it, just remember how pKa influences acidity basicity, because there'll be some questions where they ask you in terms of pKa, and then it's important to know that instead of the terminology of acidity and basicity. So like what we had just talked about was like induction forces. So here's question number 4 on page 2 of the practice exam. I think this one might be good to go over. So this is what he has. OCH3. Then there's another one with an NH2. And you guys can start working through this already and trying to figure out which one's going to be the best. What's the question? It's asking for the strongest acid. And the last one looks like this. So our job here is to figure out which one is the most acidic. And looking at them, they're all the same in terms of this end right here, where the hydrogen is actually going to lose. It has some resonance going on. It has the same exact atom at each one. It's an O for each one. And it also has the exact same pattern of resonance that's going to happen. So that's not, kind of the issue that we're talking about. If you look at it, what's the only difference between all of these? It is the atom that is up here. So we know that this is going to be an induction force one, right?
Mm-hmm.
So looking at this, which one is going to be the most acidic? And induction force is based purely on electronegativity.
F is the most electronegative.
Yes, F is like by far the most electronegative thing on the periodic table. So the one with the F is going to be the most acidic. And then after that, we have the question that I actually just explained before about resonance and about how you have the 2 cyclohexanes and you have, when you lose your hydrogen from this one, it's not going to create a resonance, because what happens is that we lose the hydrogen, we have lone pairs, this one comes down, but that's just going to give you this. There's no need for anything to move around. It can stay just as it is. But in the same exact example, where we have an OH, but we only have one double bond and it's right there, what happens is that losing the hydrogen gives you, you're going to make a lone pair, but that causes this double bond to move. So what you get is you get the double bond having moved, which is the important part. So this one does have resonance.
So I have a question.
Mm-hmm.
Do you kick H's off when this resonance structure happens? Because if you notice, like in the last one of the one on the bottom, the carbon that is 1, 2 away from the O, So like the part that didn't have a double bond on it before and now has a
Mhm.
double bond attached to it, now only has like one space where it could potentially hold a hydrogen? Or is it just like it's generally delocalized inside of that circle?
It's about delocalization. So the fact that something has to move in order to accommodate that is what makes it resonance. Um, but wait, so you're talking about the hydrogens within the cyclohexane?
Yeah. Because the first one makes sense with the one that's on the left, it like
Yeah.
immediately to the left of the one that's attached to the O. But the one that's on the bottom left, that's not immediately attached to the O, previously definitely had two H's on it in our original structure, but now has a double bond and then
Oh,
a
okay. I
single
see what you're
bond.
saying. Yes, yes,
Yeah.
yes. So basically, what Julie's saying is that here we had two hydrogens on this carbon right before, but now it only has one. But if you look at it, everything. So originally we also had what, a hydrogen here, right? Do you see
Uh,
that?
no, because
Oh,
octet
sorry,
rule
sorry,
is
not there, sorry,
filled.
not there, not there. So we don't have a hydrogen there, right? And also we have no hydrogens here, right? So you have to look at the hydrogens overall. But I think that, oh wait, I see what you're saying. So there was no hydrogens. So there was one hydrogen here, and there remains one
Yep.
hydrogen there. Yeah,
Yep.
okay. So you're saying the
So what
hydrogens
happens to the
shift.
other hydrogen? Is it
Um,
like a positive charge over there
no,
or something?
no. That's not, yeah. In resonance, there doesn't have to be a positive charge to delocalize it there. Um,
Okay, so it's just like delocalized generally in the entire circle.
yeah, yeah. And like,
Okay.
yeah, and remember what I said about like before, and when he asks you about actual resonance questions, you should never like try to like delocalize a hydrogen to do that. Um, but I guess everything's changing in this situation. Like you're losing a hydrogen to begin with from the OH. So it's not like they have to match up in terms of the actual molecular formula. Because we're talking about before the hydrogen is lost versus after the hydrogen is lost from being an acid.
All I know is that this is definitely oxidation.
Yes, I would
I
agree.
have I have no idea what else is going on over here. I'm so sorry.
I've noticed in general, like, it seems to be oxidation if you go from a single bonded oxygen to a double bonded oxygen, because you have to lose hydrogens to do that, right?
Yeah,
Not necessarily from that exact carbon, but from somewhere you have to lose hydrogens.
somewhere.
Yeah. So, okay, so moving on, he asks about like dipole moment, that kind of stuff. If you draw out your Lewis structures, you'll see. I personally think he doesn't give enough area, like enough room in this question for you to do your Lewis structures. So I'd recommend maybe like having a piece of paper on the side where you can do your Lewis structures out because there's not enough room on the actual exam, or maybe on the page with the periodic table or something like that. Okay, the next one's about basicity. I think we can skip that. Some more Lewis structures. Boiling point. So another factor of boiling point that's really important is OH bonding. So the more OH bonding you have, the higher the boiling point. Because basically the OHs can kind of create hydrogen bonding with the waters. So in this problem, question 9 of, so it's the third page, question 9 of practice exam. We have some structures, and sorry, my handwriting has gone completely off the walls, and that's because, and I'm trying to keep it, at least somewhat legible, but it's basically my hands are cold right now, so it's not looking good. Um, so this is what we have here. Um, So when you look at this, first of all, they all have the same number of carbons, right? Yeah, they all have the same number of carbons. But the difference is that there's some branching going on in this one, and also there's some OH bonding going on in these, and there's more OH bonding in that second one. So if we label these A, B, C, and D, basically, if we list them from high to low, D would come in at the lowest boiling point because, or no, sorry, A would come in at the lowest boiling point because the more branches, the lower the boiling point, right? So this one is very branched. This one is unbranched, so that would be D right here. But between B and C, so OH bonding is like really important in making the boiling point higher, because it can stick to the waters and it's less likely to break apart. So the more hydrogen bonding, the higher. So C is going to go here, and then B is going to go here. So more H bonding equals higher boiling point. All right. The more hydrogen bonding, the higher the boiling point. So C is going to be highest, then B. Then between A and D, it comes to our other rule about branching. So the more branches, the lower. So A is the lowest, D is the next. Okay. Resonance structures, blah blah blah. I think we can go over this one because like it never hurts to go over more resonance structures because they are like probably the thing that I think is the hardest about this exam. So we have a lone pair on our nitrogen, a double bond right next to it. So they're saying what is what is a possible resonance structure for this? So as always, like you could just take your lone pairs and move them around. So let's just take our lone pairs and go. Oh, just red. Yeah. So take our lone pairs and go bam like that. But then this causes that one to go here. Also, one thing that's to be noted about this one that I just forgot about, there's a positive charge here. So that takes care of that hydrogen issue. So like in general, from what I've noticed, you're not supposed to eliminate any hydrogens in these type of questions where he's outright asking you, what is the resonance form of this? Don't eliminate any hydrogens. But in general, like when you're talking about acidity and stuff, we're not supposed to worry about that. So this is going to just form this structure where we have, again, like our 6-membered ring, and there's going to be a double bond here and a double bond here. And there's going to be a plus charge on the nitrogen, though. Because nitrogen likes to have 5 things attached to it. Oh, so something I guess he forgot to add here is that there's an H on the nitrogen. There's an H on the nitrogen. And you know
Yeah,
that
that
though,
makes
because
sense.
you don't need to, like, he doesn't need to have drawn that because he didn't put a charge there. So you know that there's an H there. So assuming that the H remains attached there, that gives it a positive charge. Because nitrogens like to be attached to 5 things. Okay, cool. Do you guys want to do the one right under that? I don't think it can hurt to do too many resonance structures. Let's do this one. So, in this one, he's asking for a resonance structure of the following. So, here we go. So that's what we're dealing with. So a resonance structure for this, like again, we just want to take care of those charges. So um, we'll take this lone pair, bring it onto there. Again, you don't want to bring it onto this side because that will force a hydrogen out. And then what happens is that we can just bring this up. And what that gives us is it gives us the double bond there that we formed, but then an oxygen that only has this. Now, one thing that's missing is the negative charge here. Make sure to always draw your charges the way they should be. So that takes care of that negative charge in the carbon. And if you think about carbon versus oxygen, oxygen prefers to have a negative charge over carbon because oxygen is more electronegative. If we, from the periodic table, CNOF, so oxygen is more electronegative because electronegativity goes that way in this direction. So oxygen is better to have a negative charge than carbon. Okay, this is good. This is kind of what I wanted to go over now. So basically, page 3 of the practice exam, we have constitutional isomer questions. We have C4H9Br. And so something that's really important here, there's so many important factors when you're doing this kind of question. But overall, first let's figure out if there are any degrees of unsaturation. So we know that there's 4 hydrogens. So with 0 degrees of saturation, it would be C4H2 times 4 plus 2, which gives us C4 and H 10, right? So this would be with 0 degrees of unsaturation. But here we're dealing with C4H9Br. If you guys recall, Br counts as the addition of another hydrogen. So this equals C4H10 because Br is just one more hydrogen. So if you remember like our little list, Brs or halogens in general, so X is equal plus 1. I cannot remember what the other ones are. Do you guys remember? It was like N.
I have it written. I have N is -1H, and S and O are 0 H's.
Okay, so N is, thank you. So N is subtract a hydrogen. X, so any halogen, is add a hydrogen, and S and O are just 0. They don't impact the hydrogens at all. So, and this is something that's really important for Orgo 2 to remember this. So just keep that in mind and keep reviewing that. So we have the Br counts as a plus 1, so that's C4H10, which, as we can see below, means that there's 0 degrees of unsaturation. So we can use that to start drawing our structures. So one thing that I like is I like to start from the longest chain and then work down to a smaller and smaller chain. So assuming a longest chain here of 4, right? We can attach our Br maybe to like the end here, right? I'll do that in green. We could also do the same thing, a chain of 4, but we could attach our Br to a different carbon, so like this carbon right here. And what's a really important factor for this is to not repeat the same molecules. So let's say I was to continue, if I didn't know, I could continue and be like, oh, what about if we put the bromine here? No, that's the same thing as these two are the same thing because it's just a bromine on the second carbon. See, this is carbon number 1, this is carbon number 2, this is 1, and this is 2. It's just a bromine on the second carbon. It's the same thing. So that one is just a repeat of the same structure. Also a repeat of the same structure is if I did the same thing, but I attached the bromine on this end. That's just the same thing as this. It's just Br on the first carbon. So make sure you're not repeating any structures because that will cause you to lose points. So those are the 2 structures with the longest chain, and then I like to go to the next longest chain. So a next longest chain would just be a chain of 3, right? So we can think of all the places to attach a bromine at the 3rd one. So if we have a chain of 3, then we know that there must be, 1 more carbon to make it 4 carbons overall. And we can attach our bromine to here. And if you tried to attach the bromine to this one instead, you would see that's still the same structure. These are both the same. It's just flipped around a little bit, but essentially there's a chain of 3. There's a chain of 3, right? And then the bromine is 1 up from that attached to that thing, right? So it's the same thing either way. So erase that. That's not going to count as one of our structures. Then That's our only structure possible with a chain of 3. Now let's do a chain of 2. Oh wait, no, never mind. What if we did this? Same thing, but we attach the bromine here. Right? That counts as 1 as well. And I mean, we could try a chain of 2. So if we tried a chain of 2, I mean, I don't really see how that's possible. Yeah, that's not possible. So there's no such thing as a longest chain of 2. So those are our 4 possible isomers. I don't think there are any other possibilities for this. And then he might ask you which one is most fitted for SN1, for example. What do you guys think? Which one is most likely to go SN1?
I think we just had a question like this on our latest exam. I think it's the last one because it's tertiary alpha carbon.
Yes. So like on your last exam, he asked you guys a question like this, and basically what it is that in the final, yes, you're gonna be asked the stuff from exam 1, but it's gonna be changed up. You know? It's gonna be changed up. So it's gonna be changed from, it's not as base as it used to be. He's gonna introduce some new stuff to it. So that's what this is basically a kind of question that you might get. So look out for that. He could also just say which one is most fitted for SN2. In that case, what would you choose? Mubaraka.
Yes.
Which one would you choose if he said which one's best for SN2?
Number 1.
Number 1, yeah. So this one is best fitted for SN2. Okay. So I just realized that we went way over time. For some reason, I was thinking we were going to end at 4:30, but we're actually supposed to end at 3:30. So I think we're just going to end this now. So what I would say is just continue reviewing for exam 1. I won't do another full-blown exam 1 review. But we've pretty much reviewed everything now, except for chair confirmations and Newman projections. So I can arrange to do a review of Newman projections and chair confirmations during the last week or during the reading week or something like that. But what I think to continue your review of exam 1, just go through everything, all your practice exams, all your practice quizzes, all your exams. And if you have any questions, write them down on a list, and you can either send it to me immediately and I'll keep it for next time we do a review, or you can just bring it to next time I do like an open review session where we're just asking questions and stuff. For now, do you guys have any questions though?
Not right now. Thank you so much.
Okay, yeah. So enjoy the rest of your break. Enjoy the rest of your break, and try to review stuff before the review sessions. So tomorrow we're going to be doing exam 2 review, same time, 1:30 to 2:30, or 1:30 to 3:30.
Thank you.
Thank you guys
Thank
for
you so much.